So what we have here at the start of chapter 3 is a revision, largely, of stuff you've seen last semester in MATH6040, a little review of differentiation. And it'll be a little bit extra, so you should watch until the end. And probably some things I'll go over relatively quickly. Okay, so the objects that we study here are functions mostly. We spoke about functions briefly in the chapter on matrices. Matrices are like functions. They take in a list of numbers and they send out a list of numbers. A vector is sent to a vector. Now the ones we're going to probably be interested in for the moment, but this will change, would be things that take in a number and spit out another number. So for example, f of x equal to x squared. You spit in a number, you substitute in you input a number and it spits out the square of that number. So for example, 3 in, 9 out. That. Now, what you studied those, pretty much everything in MATH6040, your maths from last semester, was studying such functions, number in, number out. Now, you were interested in all kinds of combinations of such functions. Now, we'll give you the basic kind of building blocks of these functions. You have constant functions, lines, multiple of x plus a constant, quadratics, anything with an x squared and perhaps an x and or a constant. Polynomials. Now, polynomials is just where you've got any power of x. So actually, lines are polynomials and quadratics, but in general, higher powers of x are also polynomials. Powers on their own, for example, root x, which is x and a half. Trigonometric functions, sin x, cos x, tan x. So these are all things you put a number in, you get a number out. Inverse trig, exponential, and log. And what you studied were combinations of these. So what I mean by a combination is a sum of functions. For example, sin of x plus minus 3. Scalar multiples. So say the power function, the cube root of x times 5. Differences, well, that's the same as sums really. Products. So you take two functions, say the cubic or polynomial x cubed multiplied by tan of x, that's a new function. Quotients, for example, the inverse sine of x divided by root x. Powers, now this is taking a function and then taking power of it. For example, the polynomial x to the 4 plus x cubed, power minus 3. Roots, which would probably also come with the powers. For example, take the function log of x and combine it with the square root or the x to the half function like this. And compositions. Now a composition is the most complicated one, the one you need the chain rule to differentiate. Maybe we'll just write down something here. So when you take things multiplied together, you need the product rule to differentiate them. Remember, differentiating a function, the derivative gives you the slope of the tangent all day long. All you should actually know out of MATH6040 for sure is how do you find the slope of the tangent to a curve? You differentiate it. To differentiate functions that are multiplied together, you need a product rule. If they're divided, you need a quotient rule. And then this last one, the compositions. So compositions are a little bit trickier. We did speak about them in matrices. Matrix multiplication is like a composition. So when you multiply matrices together, well, what happens is you have a vector, list of numbers. The first matrix sends it to another list of numbers, and you give that second list of numbers the output from the first function as an input to the second. And then you input that into the second function, you get something else out. For example, here, a number x is sent to x squared plus 3x minus 2. So this is an output, and then that's used as an input for sine. And this is what's called a composition, and to differentiate these, you need the chain rule. Now, how to differentiate all of these and various combinations and graphs and stuff of the functions on the top, there is a catalogue of notes, a function catalogue at the back of your notes, which will explain all this. Now, as I said, all you need to definitely know after Tech Maths 2, MATH6040, the maths you did last semester, is that the derivative of a function gives you the slope of the tangent to the curve. That's the most important thing. That's what you really need to know. So that's what the derivative is. Now if we take a function that's most of these elementary functions are smooth. What that means is if you zoom in on them, they look like lines. For example, if you take the function log of x, which does something like this, so at x equal to 1, log of 1 is equal to 0, so you plot the point x equal to 1, y equal to 0. Near this point, if you zoom in here, this looks like a straight line. And the line that it looks like, that is what the tangent is. It's not about hitting the curve at a single point. It's about looking like the curve near a point. And as it turns out, log of x close to 1 is approximately equal to x minus 1. And you can do that, you can mess around with your calculator. Log of 1.1 is approximately equal to 1.1 minus 1. Now, if you want to find the equation of this tangent, you need a point and a slope. You will have a point because you'll know the point you're interested in, and then you'll have to get the slope. And this leads to the derivative is the slope. So the slope of the tangent is given by the derivative at that point. And this allows you to approximate functions using lines. So that's the first thing. Now the second thing is that derivatives give you rates of change. Now, let's see how we can do this. Now, this graph probably isn't set up perfectly, but we'll go at it. Suppose you have a function that describes the temperature of a cup of tea in an ambient temperature of 20. So suppose here, so this should probably be T, temperature. It's going to start at, shall we say it's 100 degrees, and it's going to cool to 20 degrees. The graph will do something like that. As x, which is supposed to be time, I suppose, as x gets bigger and bigger and bigger, the temperature of the tea gets closer and closer to the ambient temperature of 20. The heat exchange going on. Now the question is, can we say, looking at the graph, is the temperature increasing or decreasing? And well, of course, looking at it, you say, well, the temperature is decreasing. That is because the slope is negative. So if we take a particular point here, the slope is negative. And it turns out, we won't go through this stuff from last semester, the rate of change of a function is the derivative. So if the derivative, which gives is the slope is negative, if the derivative is negative, same difference, then the function is decreasing. A negative rate of change is decreasing. So you can analyze a function like that. If the derivative is negative, it's decreasing. If a function, if its derivative is positive, it's increasing. And using those ideas, then you can go off and maximize and minimize a function. So suppose we have a function looking like this, maybe some class of cubic. You can look at the turning points and say, at the turning points, the derivative is 0. Now, you can also kind of talk about that in language of rates of change. The derivative cannot be positive here. If the derivative was positive at the maximum, that would mean the rate of change was positive. That would mean the function is increasing. But if you're at the top, you can't be increasing. Think about it. When you're at the top of the mountain, you can't go any higher. And similarly, the derivative can't be negative. The rate of change can't be negative. When you're at the top of the mountain, you're not going down, because if you're going down, you've gone past the peak. So the derivative can neither be positive nor negative at a max or a min. So the derivative must be equal to 0 at these. And then you can go off and look at the second derivative to decide. It's a little counterintuitive. On this one, the second derivative is negative, and in this one, the second derivative is positive. You can, if you want, childishly say this is happy, positive, sad, negative. And in fact, you can tell the sign of the second derivative by looking at the function like that. Whenever the function is sad, the second derivative is negative. So anything like that, the second derivative is negative. Anything like that, the second derivative is positive. Indeed, if you do it with x squared, the second derivative of x squared is 2, which is positive, so x squared is a happy u. And if you look at minus x squared, the second derivative is minus 2, which is negative, so a minus x squared is set. And the last thing where this is very, very useful, differentiation that is in solving and analysing and setting up differential equations. Now, we're not going to do any differential equations here. You would have done it, would have been the last question on your MATH6040 paper, but it's going to be absolutely mega in third year. Yeah. So what have we got? So for example, something like anytime you have a rate of change proportional to x, you get something like this. So radioactive decay says the amount of stuff that decays is proportional to the amount you have. So it might be, say, 1% of it decays every hour or something like that. Or also exponential population growth, if you said that the population growth is proportional to the amount of people you have. For example, the growth rate might be, I don't know, I have no idea, 2% in a year. You get these as differential equations. You're trying to find quantity, something like this. So these differential equations. And now, in all of these, you need to be able to differentiate a function, and you need to be able to differentiate all combinations of them. And this is what you're doing in MATH6040. And I'm just going to write up all of these. So the sum rule is pretty easy. If you're differentiating a sum, you do it term by term. If you're differentiating a constant times a function, you fix the constant and differentiate. These two things together are a very important property called linearity. So differentiation is linear. You can differentiate term by term if it's a sum, and you can fix constants. The difference rule is basically a combination of those. You've got your product rule when things are multiplied together. You do the first by the derivative of the second plus the second by the derivative of the first. And you also have this quotient rule. It is what it is. And then the chain rule, which is the hardest. Now the chain rule is the one that you will forget, and unfortunately we're not going to push you too much in the chain rule in MATH6040. It will arise, and whenever it does, we'll do it properly, but it's not ideal. When you go into third year, you will have not seen the chain rule done very properly for perhaps 18 months. I can only really apologise about that. This is something that I think we should be working on. Basically what happens is we have these new types of differentiation, and we kind of focus on them, but really you want to be practicing the normal differentiation as well at the same time. All these formulas, of course, are in the tables, and there will be a test on this chapter, and I will give you that test.